So we talked a little bit about this last time as well. Another type of decision problem is classification problems. So you can think about taking the umbrella as a very particular type of classification problem. Don't care only about predicting the range, you care about specific decisions you make. And different types of decisions have different outcomes. Different mistakes have different results, bad or good. Yeah. So a similar thing you can say that is a classification problem where instead of having stations, let's say weather stations reporting stuff, you actually have some models that predict labels given previous data. Yeah. And each one of the models is different and you have to guess the right one somehow. Yeah. And I don't specify yet what these models are, but in general it's the same idea as for the rain example. You simply have a probability for every model given the data, and each one of the models gives you probability for the class label given the current observations, and then you have a utility function, and then you just use the action maxima as utility. Now this is fine, right, as long as you can actually calculate this and that. If the number of models is finite, then you can always do it. There is no problem at all. Yeah. But if it's infinite, then you have a problem. Okay. So if it's infinite, then this marginal thing that we have, this sum, is basically an integral. Yeah. And calculating the integral is generally difficult, right? That's one part of this thing. The other part of the problem is that our belief, in this case, was represented by a vector, right? It has 3 values. But now our belief, because it's defined for an infinite number of models, it's a function, it's a real function. Yeah. So now you have to go from one function to a new function. And basically you multiply one function with another and you get a new function. That's not always something you can do. Okay? When you can do it, then this type of model is called conjugate. So, and then you have a new function in the same family and everything is nice and simple. And we saw a very simple example of that in the coin tossing. So then in the coin tossing, there was one function called the beta distribution, and it has 2 parameters only, and then when you observe data, then you just change these parameters when you do this multiplication. Yeah? But these very specific examples. And these examples are almost all of them in what is called the exponential family of distributions. Okay? And you can put it another way, you can say that what the data says about the models can be expressed in this particular case with a finite dimensional sufficient statistic, which is basically your belief. And every time you have new data, then you can represent the same thing with the same dimensional sufficient statistic. So how much you have learned about the models from the data. Now, in the general case, this is not true anymore. You might have a simple function representing your prior belief, but then when you get data, because you have an infinite number of models, you end up having a very complicated posterior belief. And the only sufficient statistic for what you have learned is the data itself. You cannot really throw away any of the data. You don't summarize the data by some numbers. Okay. So what we do to avoid that? Well, one thing you can do is, I mentioned before, that if you have one of these models, let's say it's raining all the time, so this model will have very high probability after some time. So you could then say, okay, I will throw away all the other models and just look at this one. Okay. This is what is called the maximum posteriori approximation. So you approximate the marginal distribution, which is an integral, by the maximizing member of this integral. Okay, the point which has highest probability. So if you look at it in terms of a curve, so it doesn't matter what you're trying to maximize. You have to make some decision, and this is your distribution over the models, and well, if you approximate this curve with this curve here, right? That was the one point that is non-zero. Then the sharper this curve is around this point, then the better your approximation is going to be. Basically. And this is the idea of maximum posteriori approximations. Now, this trades one problem from another. So instead of calculating this complete curve, now we have to find the maximum of this curve without having calculated the curve. Right? So normally using Bayesian inference is, let's see, okay, let's start with different slides here. So you can decompose this in two different ways, but I'll show it here. So we saw the coin model, right? You have a prior distribution for coin tosses, and you observe some data, and this gives you a different likelihood function. So this is this part here for every model. This is your prior, and this green thing is the probability of the data for every model. And now you multiply those two things and you get a new curve, okay, which is nice and smooth again. That's fine. So in this example, we can calculate in closed form this curve, but in general we cannot do it. So we'd like to approximate by finding the maximum of this curve instead. Okay. So how can we find maxima of curves? Does anybody know any algorithm for finding the maximum of a function? An algorithm for finding the maximum of a function. Does anybody know of one? What do you think? Okay, if you have a function that is, has only two possible values, like, so you have a function f from 0, 1 to the real numbers, okay? Now this function, how can you find the maximum? It's pretty simple, right? F of 0, is it greater or equal than f of 1, right? If it's greater, then 0 is the maximum. If it's 1, then it's another one. Okay, but let's say if it's continuous, f 0, 1 to the real numbers, right? So now, how do we find the maximum for this function? Yeah, we can take all the points. Well, there's an infinite number of them, right? Or you can use what is called a local algorithm. So let's assume that the curve is like this. Yeah. Okay, so concave. 0 is here and 1 is there. So now, if you can only observe the value of a function at some point, right? Some point x1, then if you knew that the function was increasing on that direction, then probably you should look for a point to the right. Yeah. So you have to have a notion of whether the function is increasing or decreasing in different directions. Yeah. And does anybody know of a mathematical concept where we measure whether things are decreasing or increasing? Yes. Right. So that's the mathematical concept. So in one-dimensional functions, then you say, well, just look at the derivative of the function, okay? In at some point x1, and just say that the next we go to some point x2, which is this one times, let's get called alpha. Go to some other point x2, which is in this direction. Yeah, so this is just a linear combination of the 2 points. So this is like a small vector moving to the right. Okay, so that's a basic idea of gradients. So you want to find a maximum. Well, it's not very difficult. You just move in the direction of the gradient, and you hope that eventually you stop at the maximum. Okay. There are two problems with this. The first is that you know the direction in which the function is increasing, but you don't know how far you have to move. Okay? If you move too far, then you might end up there, so it's even lower than before. If you move too close, then you make it take a long time to reach the maximum. Right? The second problem is that there might be, the function might be like this. So there's another maximum here, which you miss. So if you start from here, even if you do very well, then you stop at another point. Well, then if you want to think about that, then there's lots of algorithms and stuff that you can play with to find a good solution to the problem. But the basic idea is look at the gradient of the function, if you can calculate it. If you can't calculate it, then you can approximate it in many different ways. And then you have your maximum, or your approximation of the maximum. Okay, so now the idea is, let let's see, where is this thing? Basically, we would like to find the maximum of this posterior distribution, so the model that maximizes the posterior is defining the actual complete posterior function, and we could do this by doing grind descent, okay, grind ascent, if you want. And there's an interesting thing about this. If you look at the objective function in terms of the logarithm, so this is the original objective. If you take the logarithm of this function, right, then the model that maximizes this is the same as the one that maximizes the logarithm, because the logarithm is an increasing function. Okay? So that's nice, because now you can think about it as a sum of two terms. One is, how well does this particular model fit the data? So you give a high score to the model that fits the data best. And the other one is kind of your prior, right? But how do you use the prior? Well, one thing that they do in learning theory is to say, I will give a low probability to models that seem too complicated, or models that seem absurd. But you still put some probability in them. And this is called the regularizer in machine learning sometimes. It depends on where you come from, but that's the general idea. So you have some objective function that you maximize. It has two terms. One is data related, and one is related to your prior or your regularization parameters. Say, what do you think about the right model before seeing the data? Should it be complicated or should it be simple? Yeah. So you would like to have a bias towards simple models in general, because they generalize better. But if you have a lot of data, then maybe even a very complicated model could describe it well. Yeah. So that's why, for example, you see that these days very complicated deep neural networks perform very well with lots of data, but when they were using them in like 20 years ago with not so much data, they were not working so well. So, okay. So before we talk about classifications, problems in general, let's think about what is the optimal classifier. Okay. So, what is the optimal classifier? Let's say we have a utility function, okay? And our utility function is, let's say, the one when we classify correctly and 0 when we don't. So we want to maximize the expected number of correct classifications. Okay. So now I would like, let's say that we have a model for the data. Somebody gave it to us and says, this is the probability of seeing a particular X. This is the probability of seeing a particular label Y. So we know the model, there's nothing to compute apart from a policy for classifying things one way or another. Okay? If you had always access to this model, then it's pretty simple to do the calculation for finding the best action at any point in time. But let's say that just they give us this model, and they say, okay, calculate a simple classifier, a simple policy for choosing one class or the other from this model, and then I'll take the model away. Okay? Why is it good to think about it like this? Because when you collect data, it's like you have access to the model. You collect data from nature. This is the actual model of the world, right? And then using this data, you can then build a classifier. And then after you have done with the data that is gone, and you have your classifier, and it's finished. Yeah. So think about it like this. So we want to maximize this function. It's not very difficult. But first we have to calculate what the function is, right? So what is the function? The function is the expected utility. So for every action you can make and every actual label, there's the probability of the action according to your classifier parameters. And then the probability of the data, so the probability of X, and then the probability of the label given the data, X. Now, if you can calculate this, then you know exactly what's the performance of your classifier, right? There's a typo here, I don't know where it came from, but anyway. So the idea is that you can always approximate, right, an integral by taking samples from a distribution and plugging in the samples instead. If it's not super clear, I will probably write this, but why not? No reason to be shy. Okay. So everything here is based on this very simple fact. So we say that we care about expected utility, right? So this is what we want to maximize. Okay? And we want to approximate expected utility by taking a sum of a finite number of samples from the data. Okay? So, okay, that's fine. Let's see. Now, we know that this guy is basically equal to the sum of every possible thing that you can observe. Okay? It's basically this. If there's an infinite number of those guys, then you can just write it as an integral. Doesn't make a difference. Now, we can say that this is approximated by taking a finite number of samples where xt are coming from the distribution P. Okay? And it is approximate in the sense that if you take the expectation of this thing, let's call this thing G, then this is basically the expectation of 1 over T sum T equal 1 T U of xt. And this is, you can move this out. And then you can write 1 over T sum T equal 1 T expected value of U of xt. But expected value of U of xt is basically what we have there, right? So it doesn't depend on T or anything like that. So it's the same thing. So just 1 over T times T expected U. Okay. So that's basically what we have. So we say that this is the same, this is a good estimate, or what is called an unbiased estimate, because the expectation of this estimate for the utility is the same as the expected utility. It's kind of trivial, but that's how it is. And it has another property, of course, that we don't actually go through in detail, but if it's a bounded function, then the error that you make in your estimate is basically proportional to 1 over square root capital T. Okay? So I can just write proportional to 1 over square root capital T of the actual utility. So the more data you have, the more samples you have, the better your estimate. Okay? Fine, I think for now. So the idea is you can approximate the utility, the thing that you want to maximize here, you can approximate it with a sum of things. Okay. So the approximation can be anywhere in these two curves, for example. Okay, it will be somewhere in between there. That's fine. That's an approximation, but you can work with it. Okay. Now, this still doesn't tell us how you deal with the problem of gradients, because to use this optimization algorithm gradient ascent, you need to have a gradient, right? So, what is the gradient of this thing? Well, just like with expectations, sorry. So with gradients, we have the same idea. With gradients, what happens is that, okay, gradient descent basically says move in the direction of the gradient by some small size, and what we have here is saying we have, when our function is an integral, like here, you can approximate this step by taking a sample from the integral and then moving in the direction of the gradient only for the one sample. Yeah. So go through it again. So the idea here is that you want to get the derivative of some function f, right? But f is sum, okay? Okay, and this you can write as so here there's a parameterized function g, so the probability doesn't have any parameters, it's just fixed. Okay, So now you can basically replace this calculation by taking local derivatives for each one of the values of g of x. Okay, that's the idea here. So you don't have to calculate the complete sum here and then take the gradient. You can just look at each of the individual points in the sum and take the gradient. Okay, and if you think about in terms of what we said before about the random sampling, you can do exactly the same thing. You can say, well, I will just sample xt from P, and then instead of moving the direction of the gradient every step, I will move in the local gradient defined by the sample of x of t. So I will say that θt plus 1 is equal theta t plus alpha times the gradient of g for the xt sample. Okay. So if you think about it now in terms of a data-driven process for estimating a classifier, you don't really have to wait to see all the data until you have created your classifier. For every point that you see, you can just adjust the parameters of the classifier directly. Yeah. And this is very, very useful in online learning, but also in big data problems where you don't really want to compute gradients for the whole data. And in practice, actually, it works better to do it like this than to calculate the gradient for the whole complicated function. So there's lots of literature about that and how to do it in the best possible way in practice. Okay. Right. So that's about the optimization part. So let's go to neural networks a little bit, okay? We haven't said up much about what are these parameters or anything, right? We just said we have a set of functions that we can use to classify or to represent distributions. And let's go in two ways. As I said, you can use maximization to approximate a distribution, and that would be fitting a model, a distributional model, to the data. This is one type of objective. And the other objective would be to find a good classifier, which is a slightly different thing. So here you really want to measure to capture the distribution of the data. Here you just want a good classifier without necessarily getting the distribution of the data. Yeah, that's a different thing. So just to make things clear, in one case I will talk about y, those are the actual labels and the probabilities, and I will talk about A, the actions that you make, to say that these are your actions, this is what you assign as a class when you make a decision. And in this case you have some explicit utility. Here the utility is not defined, but typically it's something that relates to how close this probability is to the real one. Yeah. So it's some kind of negative divergence or something like that. Okay. Typically it's the negative cross entropy for classification. And this is what you actually use. Okay. So the difference between the two views is very simple. For the first one we could use standard probabilistic ideas, but it's usually very complicated because there is not a finite number of models. While the second problem is the optimization problem. Yeah, we can actually formulate this as an optimization problem as well. That's not a problem. Okay, so the simplest type of function we can use is a linear function in the infinite case. So we can say that we will have a matrix, and our probabilities or our actions will depend in a linear manner on this matrix. So the action we take will depend on what we see, right? But it will also depend on the parameters that we choose. And the actual, well, this structure basically tells us, this is very general because it could be anything, but when I say it's linear, then it means that the classifiers that we admit are very specific in structure. So in particular, let's say that we have one or two futures. So the observations we have, let's say, is a two-dimensional real vector. So here represented as x1 and x2. This is not time. This is basically one data point. And then we have two possible class labels we could assign a1 and a2. And in a linear neural network, what's called linear neural network, the dependencies are kind of like this. So a2 depends on both the inputs, and a1 depends also on both the inputs. But they have separate parameters. So this one has one set of parameters on which it depends, and this one has another. This one is still not quite clear what it means, so what you usually use is an architectural diagram. And this one basically says, well, let's split things into, well, before I go to this one, there's one other thing. So if a1 and a2 are linear functions of x1 and x2 that don't depend on each other in any way, then you have a problem. Because if you want this to be probabilities, then they might not sum to 1. So you would actually want this to be probabilities, and that means that there should be some dependence between those two things. So neural networks, or the idea of architectures for neural networks, solves a lot of this problem, because as well, think about a general function as an architecture, okay? And this architecture, you can use it to represent, let's say, different layers of abstraction for the problem, okay? So let's say these are kind of your input filters, like what you see, yeah? And you can say that the second layer, which is just a linear combination of the first two things, is some kind of representation of how important these two filters are for two different tasks, Z1 and Z2. And then these two Z1 and Z2 variables that we just added now, we combine them in some way to make sure that we have actions whose probability sum to 1. So here, this variable here is just a linear function of both inputs. And this was another linear function of both inputs. And here now we have that we take the exponential of those two, dividing by the sum. And this makes sure that we have a sum equal to 1, right? Because when you sum these two, you get EZ1 plus EZ2 divided by EZ1 plus EZ2. So it's always 1. But you can see that this kind of clarifies things on what the function that you calculate is, right? So you have one linear layer that's so-called in neural networks, and one so-called softmax layer. And this ensures now that you have probabilities here. This one is nice and simple. Why is this one? Well, it's convenient to have this linear function actually, because the gradient of a linear function with respect to the parameters is just the parameters. It's just the respect of x. So if you remember your gradient, the gradient of x times y with respect to x is just y. So the same thing here for vectors, basically. So why is this useful? Well, let's go a little bit to our original problem. We want to find the maximum of this expected utility for some data that we have observed. And we do this by taking the gradient operator and putting it inside here. But now our policy, right, is complicated because it depends in a complicated way on the inputs. So you go through the inputs to the z, and then from the z to these a's. Right? So the basic idea of neural network algorithms, most of them anyway, is to remember the chain rule of differentiation. And the chain rule says, well, if you have a function of z and z is a function of x, then if you want to take the derivative of f with respect to x, then you just put the two together. So these two cancel out, right? But that basically means you have broken down the gradient into two simple steps. So by doing this, now in our case, we take the derivative of the actual policy with respect to the parameters. That means taking the derivative of the policy with respect to the output z, or the function g, which is z, and the derivative of g with respect to theta. And then when you combine this together, the calculations, the way they look like is that you have some error terms here, and the error terms that you have here kind of depend on these error terms in the future. So it's an algorithm that when you write, it kind of back propagates errors. And that's why they call it back propagation. But basically, classification, or in general, neural network algorithms that use gradient descent are basically applying the chain rule together with stochastic version of gradient descent or gradient ascent. So instead of doing exact gradient computations, they use stochastic gradient computations. And then, because everything is in has a simple architecture, then that means you can always do a so-called chain rule. And that means that every computation can be local. So you don't need to compute everything everywhere in the network at the same time. You just compute a gradient here locally, another gradient here locally, and then you go backwards, compute another gradient here, and another gradient here, and so on. So you can have a super complicated neural network, and it doesn't matter. The algorithm is the same. Okay? There are some problems with that. For example, if you have too many layers like this, then sometimes the gradients become very small as you go backwards, and then nothing changes in the first few layers. but let's go through that. And the other thing is that, so why would you want more layers in your network? What do you think? Let's say you want to build a classifier, okay, and you have two functions, two data types like this, okay. So the thing is that because of this linear structure here with one layer, there is a set of points whereby these z's are all 0, okay. So, and this is a hyperplane. So that means that on one side of the hyperplane you classify things as one class, and on the other side of the hyperplane you classify things as another class. And this is fine, but it could be that your class structure is complicated, so it's like this, for example. Then in the original space, in the two-dimensional space that you observe the data in, you cannot separate the classes with the hyperplane. Okay? So typically what you can do is, for example, you can project this into a more complicated space. Yeah? And then you could separate them. That's one of the things that you can do. And another reason why you want to have more layers, so first layer you have n, and then dimensions, and then you have n dimensions that are much greater than n. And then here maybe you can classify things, and then here you can have just C layers on the last layer, which is the number of classes you have. Okay, so you have this architecture. Okay, you can have the other problem, like an image. It has millions of different features that you observe. Then how do you deal with that? Well, in vision, what they do is they do a clever tying together of parameters. So now each one of these z's has its own parameters, but in image recognition, there is this kind of idea that there is symmetries and there is invariance when you move around, translation invariance, that's what it's called. So if you see an A here, it's the same as an A there, or an A there, or a face there. Doesn't matter where it is, it's still a face, right? So what the idea is that you have these weights that are the same across many, many places in the neural network. Yeah. So there's weight sharing, so-called. The other thing why you want to have many layers is that you might have many different classification tasks. Okay? And for every task you have the same data, but you care about class differentiating different things. Then one thing you can do is you can have a neural network that has a structure like this. So you have as your input layer and a complicated middle layer, and then you have a couple of layers later that are different for two different tasks. And here, this layer in between, that is common to both different tasks, would learn a representation that is kind of general for the problem, for the data you have. That was the promise of neural networks anyway. And that's what a lot of people are using neural networks for, at least the deep ones. Okay. So now the problem is that if the neural network is too complicated, it's difficult to train all these parameters, to find the parameters. Yeah. So we still are not out of the woods, I would say. So let's see. There should be something here. Yeah. So there is a small notebook I have, which talks about, it's called random projections. So one idea that you can have is, well, random projections. So instead of saying that I will train in a specific way my layers of a neural network, you can say that, well, I will just use a random, completely random projection, and then use a simple linear classifier at the end. Why? Why not? Actually, there are some reasons why this is good, some reasons why this is bad. Let's see. Okay, here it is. So in this specific example, come on. I have a simple multi-layer perceptron with more than one hidden layer, so it can have nonlinear projections, so it can do other things than hyperplanes. And there is logistic regression, which is basically a linear neural network. It's another name for it. And there's k-nearest neighbors. And we can run them on this data set you have seen before. So this is the wine data. It's a very simple data set. And have k-nearest neighbors, have logistic regression, we have MLP. And for the MLP, I have 3 layers, one with 10 neurons, the other with 5, and the other with 2. Okay, and then you can see the scores. And in the training data, okay, so I'm not doing a very complicated comparison here, I'm just having the training and a test set. Yeah. In the training data, you can see that if you use the raw data, then your best performance is with K and N, okay? And in the test results, the best performance seems to be with logistic regression. Okay, it's not necessarily that a more complicated neural network will be better, right? If you have not a lot of data, then usually a simpler model is best. So in this particular case, k-nearest neighbors and logistic regression, which is the linear neural network, are best, right? But now let's think about what happens when you project the data from this low-dimensional space to a very high-dimensional one. If you do that, in this particular case, it's 1,000 dimensions from the, let's say, 10 that were before. You get that your performance increases quite a bit in the training set, yeah, for logistic regression. So it was 70%, now it's not linear anymore, so it's going to be 84%. Yeah, because what happens is that you project the data in such a high dimensional space that it's very easy to fit a linear classifier that will classify everything correctly. Okay. But this random projection is not necessarily good, okay? Maybe it doesn't generalize very well. So in the test data, you don't see a good performance, actually. Right? Everything is quite bad. Another use of random projections is to make things smaller. And there is quite a lot of literature about this in so-called compressed sensing applications. And there we see that you get much better generalization performance. Okay, I would like to ask you to play with this later if you want. Okay, it will be kind of fun.